Hey guys, today we're going to do one of my favorite units. It is called related rates. Before I share my notes with you, I'm just going to share a whiteboard just so you can understand a little bit of this concept, okay? So this unit is called related rates. Related rates. And if you remember, the derivative has two main purposes. The derivative is, so dy dx, that is the slope of the tangent line, the slope. It's the instantaneous rate of change. It's how fast something is changing at an instant, okay? So related rates is going to be a unit where we see some application problems, which I love. And essentially, you're going to be differentiating with respect to time, okay? So time is your independent variable, but we're going to be differentiating area equations, volume equations. You'll see several different situations. And when we differentiate, we're going to take the derivative with respect to time. So to kind of give you an example of that, if I had area equals pi r squared, and I said, I want you to take the derivative of this with respect to time, t is nowhere to be found here. So this is like implicit differentiation. We took the derivative of y squared and we said 2y and then times dy dx. It's essentially the chain rule. It's the same thing here, except nothing has a t. So you're going to basically write d, whatever variable is, dt, after every time you take the derivative of any variable. So the derivative of area with respect to time is just derivative of area with respect to time. So derivative of area with respect to time. The derivative of pi r squared, we're bringing the 2 down using the power rule, 2 pi r. And then because of the chain rule, you multiply by the derivative of r with respect to time. If I had volume equals 4/3 pi r cubed, and I said take the derivative of this with respect to time, we would have dv dt equals, bring the 3 down, the 3 and the 4/3, the 3's cancel, pi r squared times dr dt. So this is the derivative of volume of a sphere with respect to time. We could take the derivative of something using a product rule. If I had a rectangle changing and I have two variables here, I would say the derivative of area with respect to time is the derivative of this first one times the second one plus the derivative of the second one times the first one. So there are some ideas for you there. Derivative with respect to time is basically running d dt after every time you take the derivative of something. Now, in this particular unit, what gets tricky is there's many different types of problems, and it can kind of get confusing on, it almost seems like, when do I do what? So to help you with that, I'm going to share these steps. I already talked about that. These are the steps we're going to use no matter what. The general concept stays the same, even though the specific problem changes. So first, you're always going to draw a sketch if you need to. The second thing you're going to do is write down in calculus notation. This is really important. I'm going to model this the same way every time. You're going to write down d, whatever. It's going to say things are changing at certain rates, and you're going to want to make sure that you do, can't get my annotation tools. Come on, tools. So we're going to write down a calculus notation, the rates. So when you see that, if you see words like how fast, or you see changing, or you see increasing or decreasing, all of these words means you're talking about a derivative. So you're talking about d something dt. You're going to comb through the problem looking for those types of phrases, and you're going to write those things down. Then this step here is where it changes, right? An equation that relates the quantities. So step 3 is going to be different for every problem, depending on what type of problem we're at. But then you're always going to write down the rates. You're always going to write down an equation, and you're always going to take the derivative of that equation with respect to time. And then you're going to substitute the things that you know and solve for the things that you don't. So again, I'm going to stop sharing for a second, share my whiteboard, because I find it helpful to kind of show you some different equation options. So in this unit, you might see an area problem, you might see volume problems, and you might see triangle problems. There's other types of problems too, but this is kind of some big ideas for you here to kind of reference, to go back to this. So with area problems, if I'm finding the area of a square, Area of a square is side squared. If I find the area of a circle, that is pi r squared. If I find the area of a triangle, that is base times height divided by 2. The area of a rectangle is base times height. And if we're talking about the volume, maybe you're talking about the volume of a cube. The volume of a cube would be side cubed. Maybe you're talking about the volume of a sphere. That's 4/3 pi r cubed. The volume of a cone is 1/3 pi r squared h. The volume of some type of rectangular prism is the area of the base times the height. Those are some ideas to get you started. Triangle problems, okay, there's a few different ones here. A lot of times we're talking about distance. If you're talking about distance or the ladder problem, and I will explain this to you later, you use the Pythagorean theorem, x squared plus y squared equals r squared. So, and one of these might be a constant variable where you can use a number, and I'll explain that more. And if you're talking about an angle of elevation problem, then that's when you use SOHCAHTOA. Hopefully you kind of remember SOHCAHTOA from pre-cal or from geometry. So the idea is that you write down sine of theta as y over r, or cosine of theta as x over r, or tangent of theta is y over x. And then sometimes we do a shadow problem. That shadow problem is very classic and it has similar triangles where you have the person's walking, there's a shadow, and then these heights are constant values, and you set up similar triangles. So you say y is to 5 as x plus y is to 20. And I'll explain this more, but this is kind of a one-stop shop. You should take a screenshot of this. I will save it and upload it for you. But so you're going to pick one of these formulas to relate the given problems. Every now and then that's just an equation they give you, and they talk about x and y changing, which is the first example. And then after you have the problem, the equation, you're going to take the derivative of the equation. So just to give you a few examples, then you would say dA dt is 2s ds dt, or dA dt here is 2 pi r dr dt. dV dt here would be 3s squared ds dt. If I took the derivative here, it'd be 2x dx dt plus 2y dy dt equals 2r dr dt. So basically you're taking the derivative of everything using the power rule or the product rule if applicable, and you're always writing d whatever variable dt after it. So keep that in mind as we work through the problems, okay? So the first example we have is a little different. It says a point is moving along this graph. So this is slightly different. In the graph, it gives you the equation. So that's kind of nice, actually. I just gave you the equation. Wait, where's my Zoom? Sorry, it always takes away my tools whenever I change the screen. All right, now hopefully it's back. Okay, so let's write down our step. And we're going to comb through the problem first, and we're going to see where it says increasing, decreasing, changing. We're going to write down those rates. So I see the phrase x is increasing at a rate of 4 centimeters per second. The way we write that down in calculus is we write dx dt means equals 4 centimeters per second. We check our units because that should help us see centimeters per second. Find the rate of change. And the rate of change, so that means find something, d something dt equals question mark. Find the rate of change of y, okay, when, every time they write the word when, I do a slash, when x equals pi over 6. This is the way I set up every problem. I write down the given rate, I write down what we're looking for when we're at some value. Then you write down the equation. Well, in this case, they gave us the equation. Then I like to add a step. I like to pause here and say, are all my variables accounted for? And what I mean by that is when you take the derivative, you're going to get dy dt and dx dt. Do I have dx dt on my paper? Yes. Do I have dy dt on my paper? Yes. So now I can proceed. Another thing is I don't ever plug in anything after this when value until after the derivative. So you're going to do the derivative And then you're going to plug in. I always say it's like Dr. Pepper, dp. Okay, remember derivative, and then you plug in. Don't plug in this constant now. Take the derivative with respect to time. Derivative of cosine is sine of x, or negative sine of x, times the derivative of x with respect to time. Now we get to plug in things because I've taken the derivative. So now I'm just going to plug in what is x at this instant? Pi over 6. What is dx dt? 4. So it's going to be negative sine of pi over x times 4. And sine of pi over 6 is right here. The sine value is 1/2 because it's up a little bit. So that would be negative 1/2 times 4. So the answer would be -2 centimeters per second. Okay, let's do another one. The radius of a sphere is increasing at a rate of 2 inches per minute. Remember, the first step is to write down the information. Draw a picture if you need to. This one we don't really need to. Increasing at a rate of 2 inches per minute. So what is dr? So dr dt is 2 inches per minute. Find the rate of change of volume. So find dv dt when r equals 6. Now, this point is where I need to find the equation. Okay, and the equation is from that list of equations I just gave you. So what's the volume of a sphere? That is 4/3 pi r cubed. Do I have dv dt? Yes. Do I have dr dt? Yes. So I can plug in my stuff. I'm sorry, no, I can't. Take the derivative and then plug in your steps. So dv dt is, bring the 3 down, pi r squared dr dt. Now, after I take the derivative, then you get to plug in your stuff. This means after. Okay, touch this after you take the derivative. So that means dv dt, I don't know. 4 pi, what is r at this instant? 6 squared. Dr dt is 2. So then I can just multiply 6 squared, 36 times 2. What is that? 36 times 2 would be 72 times 4. 288 pi. Volume would be measured in what? Let's see, inches is what our unit is, so inches cubed per minute. This is the rate of change. This means change delta volume over delta time. Let's do another one. A conical tank, these conical ones are always a little tricky. A conical tank has vertex down. It has a diameter 10 feet at the top, and it's 12 feet deep. So this one is helpful to draw a picture. So I'm going to draw a picture. It says the diameter is 10 feet. And it says that this is 12 feet. Water is draining out. Okay, if there's water that is draining out, what's happening? Is this getting smaller or bigger? 10 cubic feet. That is, cubic feet means change in volume. So that's dv dt. And it is negative 10 cubic feet per minute. We know it's volume because of this cubic feet. Volume is measured in cubic feet or cubic something. And draining out means we have this negative. What is the rate of change of the depth? So that is asking for dHdt, question mark, when h equals 8. So I have my picture, and then I have my given, and now I got to come up with an equation. So we basically have similar triangles in this cone here. We have the height of the water, which is changing, and the radius of the water, which is changing. I'm not going to label this 8 because it is not always 8. So on your picture, things that are constant can have a number, but things that are changing need a variable. That is very important because if you use your picture to write an equation, you need to make sure you use a variable if it's changing. So now I'm going to relate these things. So this radius then would be 5, right? And this height is 12. So I'm going to write down my equation actually of a cone is 1/3 pi r squared h. Now here, remember I said to pause. Do I have a dv dt? Yes. Do I have a dr dt? No, I don't have a dr dt. That means it's best to try to substitute in for r. So in these cone problems, you want to substitute in for r. in terms of h. You don't get to plug in a constant because it's changing. But what you do is you use similar triangles to figure out the relationship, the proportionality here. So r is to h as 5 is to 12. And if I just multiply by h, I see that the radius is always going to be 5/12 the height. And I'm going to substitute that in to make it, so one, I don't have to use the product rule, and two, I will have enough information to solve the problem. I'm not going to get stuck. So volume then is equal to 1/3 pi. Instead of writing r, I'm going to write 5/12 h squared times h. So then I got 1/3 pi, 5 squared is 25, 12 squared is 144, and h squared times h is h cubed. I don't ever multiply 1/3 in because when I take the derivative, the 3 is going to cancel with the 1/3. Now I can take the derivative. So now I'm going to write in a different color. When I take the derivative, I get 1/3 pi, oops, no, I'm sorry. I'll bring the 3 down. I get equals 3 times a third, so those cancel, pi 25 over 144 h squared dh dt. At this point, I can plug in this. H is 8 and dv dt is -10. And I'm kind of running out of room here and things when I move it up, all my writing erases. So I'm going to try to squeeze this in. Let's see, I'll squeeze it in over here. So dv dt is -10. I have pi times 25 over 144, and then h at this instant, that's okay, I can touch this because it's after the derivative, 8 squared dh dt. And then to solve for dh dt, all I need to do is multiply by 144 and divide by this stuff. So I'm going to multiply by 144 and divide by 25 pi 8 squared. Okay. You can put this in your calculator if you wish, or you can simplify it by hand. Just make sure that you're dividing by all three of these terms. Does it make sense that it's negative? Ask yourself, common sense. Does it make sense it's negative? Yes, because what's happening is that height is going to be decreasing because water is draining from the cone. Okay, so kind of to recap the steps, write down the given, you write down an equation, you pause, you make sure all the variables are accounted for. If not, you need to substitute in terms of an equation, not in terms of a constant, because everything is changing here. So we got the 5/12 h by doing 5 over 12 is equal to r over h. We then simplified here, and then we took the derivative. Then we plugged in the things that we knew, the -10 and the 8, and then we divided and multiplied to solve. So let's try the next one. A 25-foot ladder is leaning against a wall. This is a very classic problem, okay? A 25-foot ladder is leaning up against a wall. Also, it's very helpful to draw a picture in this situation. So the ladder is 25 feet, and that is not changing. So I get to label this because this is constant. But the ladder is what? It says the base is being pulled away. At what speed? Let's see. 3 feet per second. I'm going to call this x because it's horizontal. So that means dx dt, and it's being pulled away. So is x getting bigger or smaller? Bigger. So that means it's positive. How fast? You see how fast that means d something dt. That's dy dt equals question mark when the base is 24 feet. So that would be when x is 24 feet away. So this is Pythagorean theorem because we have 3 sides of a right triangle. So it's x squared plus y squared equals 25 squared. I can write 25 because 25 is not changing, whereas x and y are. So I don't want to plug in the 24 here because it's not always 24. So we're going to take the derivative because I have a dx dt on my paper and I have a dy dt on my paper. So 2x dx dt plus 2y dy dt equals 0. Derivative of a constant is 0. Now I can substitute in things I know. 2 times after the derivative, I can plug that in because 24 dx dt is 3, 2y dy dt. Now in this particular problem, there's a few instances where you'll come across a problem where it seems like you don't have all the information. They did not tell us y equals blank, but we can figure it out. So sometimes you have to think about what's happening at this instant. I like to draw an at this instant box because I don't like to leave it on here in case I need this picture for other things. At this particular instant, this screenshot in time, X is, I don't know, oh, it's 24, and this is 25. So what is Y? So what is Y? I believe it is 5. Because it's a triple, right? 5, 24, 25. Oh my goodness. Okay, so what are we gonna do here? We're gonna see, I'm gonna plug in that 5. You could also do Pythagorean theorem, 25 squared minus 24 squared, and take the square root of that. So what's 25 squared? Let's see. 625 minus 24 squared, 576. Oh no, it's 7. Oh gosh, y'all, 7, 24, 25. I'm tired today. What was I thinking? Sorry, 7, 24, 25. So what are the triples? The triples are, oh my goodness, I knew that didn't sound right. We got 5, 12, 13. We got 3, 4, 5. 5, 12, 13, 7, 24, 25. I'm trying to remember. There's another, 8, 15, 17. Okay, so it's good to kind of remember those triples, but you can always use the Pythagorean theorem. So that's 7. Excuse my mistake there. My coffee pot stopped working this morning, so I haven't had any coffee this morning. Okay, sorry. Let's keep going. So at this point, I can multiply. That's 48 times 3, so that would be 24, 12, 13, 14, 144 plus 14 dy dt equals 0. Subtract 144, so 14 dy dt equals negative 144, and then you can divide by 14. So dy dt is equal to negative 144 over 14, or you could divide by 2. What would that be? 72 over 7 feet per second. Does it make sense that it's negative? Yes, because this would be falling, right? If this is being pulled away, this would be falling down. So common sense check is that it works out. Okay, let's try the next one. A 6-foot tall man. Oh wait, I forgot. Where is the area of the triangle? I didn't solve the other problems. Okay. Where is the area of the triangle? Hold on, let me see if I can get that back. Negative 72 over 7. Let's remember that. Okay, B, at what rate is the area of the triangle formed by the ladder changing? Okay, so this is why it's important not to change that this is X and this is Y, this is 25. Area is 1/2 base times height, or 1/2 X times Y. So I need my dx dt and my dy dt. So I solved for dy dt, so I'm going to need it for this problem, and I was given dx dt is 3. So to find this, you do the derivative of that is 1/2, and then here we have to do the product rule. Derivative of x times y plus the derivative of y times x. And now it's just a matter of plugging in things. So dx dt, they told us is 3. Y at this instant, do you remember what it was? It was 7. And then dy dt is, we saw for it, and x is, what is x? 24. And then you just multiply this out and multiply it by 1/2, and that would be your answer. And then C, at what rate is the angle theta? So this angle here. Now, you can use really any of the triangle of any SOHCAHTOA relationship you want. I'm going to use the one where we use what was given to us because they told us X, and that's supposed to be most secure. And I'm going to use it over 25, so I don't have to use the quotient rule. So if I'm using that, that would be cosine because I have adjacent and hypotenuse. So I would write cosine of theta is equal to X over 25, or 1 over 25X. Then I could take the derivative. I can say, oops, not secant, sorry. Negative sine of theta times d theta dt is equal to 1 over 25 times dx dt. Now, these always seem to trip students up. You are not solving for theta. That is not what you have to do. You're solving for sine of theta. And remember, a sine of theta is just opposite over hypotenuse. So you're just trying to solve for a fraction right here. And remember, we had that at this instant box. And at this instant, this is 24, and this is 7, and this is 25. So at this instant, what's the sine of theta? 7 over 25. d theta dt is what I'm solving for. And 1 over 25 dx dt is 3. So to solve for this, I'm just going to multiply by negative 25 over 7, by the reciprocal, negative 25 over 7. And so d theta dt, the 25's cancel. So d theta dt is just negative 3/7 radians per, is it second? Yeah, second. Okay, so in these triangle problems, if you're ever solving for d theta dt, you're never having to find theta itself. You're just trying to find the relationship of the triangle sides. So you're looking for SOHCAHTOA, one of those relationships. All right, let's try the next one. A 6-foot tall man walks away from a 30-foot tall lamppost. So we have a 6-foot tall man, and he is walking away from a 30-foot tall lamppost. I can label these 6 and 30 because they are constant. So x, he's walking at what speed? Walking away, so this would be getting bigger at 400 feet per minute. When he is 50 feet away from the lamppost, so what race is his shadow lengthening? I'm going to call this S for shadow. So we're looking for the SDT when he is 50 feet away. How fast is the tip of a shadow moving? So anytime you have the shadow problem, I always just told my kids, shadow is similar triangles. Okay, so, and it's really important that you do the whole length. So 6 is to S. Make sure your S's don't look like 5s. As 30 is to not X, but X plus X. Then cross multiply and simplify. Shadow, similar, simplify, all these S's. So 6x plus S equals 30 times S. 6x plus 6s equals 30s. 6x equals, subtract, so would that be 24s. Okay, and we're looking for ds dt. So 6 over 24x equals s, or 1/4 x equals s. Then you can take the derivative, and the derivative would just be 1/4 dx dt is equal to ds dt. And dx dt is 400. So just 1/4 times 400, so that would be 100. So ds dt, the length at which his shadow is changing, ds dt is equal to 100 feet per second. Notice we didn't have to use this. You don't have to use it in the shadow problems. And when it says how fast is the tip moving, this tip, I just remember you add dx dt plus ds dt, because that is affected by how fast he's walking and how fast this is moving. It's basically asking what's the rate of this whole side. So it's looking for dx plus s dt. So tip looks like a plus, right? You have that t, and the t looks like a plus. Add them together. So that is going to be 100 plus 400, so 500 feet per second. And then lastly, 7, at a distance of 50 feet from a pad, a man observes a helicopter taking off from a helipad. Okay, so this is a very common problem as well. Once you do a lot of these problems, you'll see they kind of repeat themselves. A man is standing away 50 feet. He's not moving. So this gets to be labeled because he's not moving. And then it says, so here's our man, and there's a helicopter facing vertically. So I need to call this something. So dy dt is equal to 44 feet per second. How fast is the distance? Okay, so they're looking for this. How fast is the distance changing? Sometimes they do angle of elevation problems here. When the man, when it's altitude, so that's when y is 120. So I just do Pythagorean theorem because it's the side lengths of a triangle, and I can use 50 because that's not changing. But I don't want to use 120 here because that is changing. You plug it in after you take the derivative. When I take the derivative of 50 squared, that's 0. This is 2y dy dt is equal to 2r dr dt. And then you can cross out the 2's, and then I can just plug in my stuff. So y is 120, dy dt is 44. R at this instant, I can do it at this instant box. This is 50. This is 120. So 5, 12, 13. So this is 130, or you can do Pythagorean theorem. So that would be 130 dr dt. And then you just divide by 130. So I have 120 times 44 divided by 130. So I can cross out the 10, and then 13 is prime. So 44 times 12, what is that? 8, 8, 4, 4, 8, 2, 5, 2, 8 over 13 equals dr dt. That's the rate at which the distance is changing, and that would be feet per second. So anytime you have that, I'm trying to think what I'm trying to say. Anytime you have the size of a right triangle, you do Pythagorean theorem. Let me share that whiteboard screen with you one more time, just so you can kind of see it now after we've done those problems. Okay, if you notice, this is the stuff we talked about, right? And there's many different types of related rate problems, a lot of different kinds. But the general idea is you write down the given information, you draw a picture. If you have a picture, make sure you label things that change with a variable and things that are constant with a number. Then you write down one of these equations, area or volume, or a distance equation, or angle of elevation equation, or similar triangles. And then you take the derivative with respect to time. Being sure to substitute if necessary, like with this cone problem, remember we substituted in for R, its relationship with H. So that's kind of the process, and make sure you take the derivative first and then you plug in the things. So just try your homework problems, and if you have a question, as always, please let me know.